So thank you, everybody, for the opportunity. I work at the Norwegian University of Life Sciences, but I'm originally from Ireland. Most of my work has been in the equatorial tropics, and I became interested in this topic just because it's so crucial in many parts of the world, of course, but this was the view from my window for 4 years in Central Africa, looking out over the forests and seeing these mists rising out of the forests every morning and thinking, where does all this water come from? So if you want to broaden the topic, of course, it's not hard to justify why we should be concerned about water. Water is basically, it's the foundation of almost everything we care about on the planet. If we care about things like food security, about health, the environment, industry, all of these things need water. When we don't have enough water, we have a problem. Now, if you look around the world, you see that water is in short supply for many people. And this is just one recent study that tells us that 2/3 of the world population is suffering from scarcity of water, too little water to actually achieve all their hopes for more than 1 month per year, and that 500 million people are suffering from water shortages this year round. Now, I often like to talk about this with people talking about climate change. They're telling us what will happen in 50 years, 100 years. We're not talking about the future here. We're talking about already. Water scarcity is a big problem. So this is right now. The majority of the world's population is suffering from a water shortage right now. So I worked for many years for an organization called the Center for International Forestry Research, and the topic of the research in that organization was pretty much trying to help poor people, trying to help disadvantaged people in the tropics to improve their livelihoods. So that was a real focus. So most of the money we got was from international donors that were trying to talk about development, and the discussion was often about development. So water scarcity was a big issue for us at the Center for International Forestry Research. And I was there in 2005 when we suddenly had a lot of emails and telephone calls and meetings because of these headlines that appeared in the papers. So here's from The Economist. This is one of the kind of well-known magazines you see in airports. And our donors were also reading this, of course. Tree planting can exacerbate drought. So basically the headline was, if you plant more trees, you have less water. And even in the scientific literature, there were headlines like this one. In Nature, it doesn't matter where you are in the world, when you grow trees on croplands, you use more water. So the message was, trees are bad. If you're concerned about water and are concerned about scarcity of water, you shouldn't plant trees, you should remove trees. So that was a big problem for an organization that was trying to look at how trees can benefit people. It's a story. So what was this all about? It was about a nice study in Science, a very impressive study, Jackson et al., 2005. And they had taken all the studies they could from around the world. That was 506 studies, so a lot of studies, very impressive. And they had looked at areas that had no forest, and then the forest had been planted and recovered, and they showed that basically in all these sites where you planted forest, you got less water. So you can see here, typically it was about 1/3 less, and in some cases as much as 44% less. And what was even worse is they were saying if you were in an area which was drier with less water, the effect was bigger. So the drier it was, the bigger the effect. So basically, again, planting trees was bad. So this looks pretty robust. It looks pretty incredible science, right? Impressive. But of course, we're researchers. We like to argue with each other. We look at the details. So we dug in a little bit, and we looked at these 506 observations. And we found that only 2 of these studies were actually in the tropics. We found that none of these sites were in areas with low rainfall in the tropics. And if we actually looked at what the species they were planting, they were basically talking about large-scale industrial plantations of just 2 genera of trees, the eucalyptus and the pines. So in a sense, very limited, still 506 studies. Okay. So what's the loophole here? Why would we think that this might not be true? Well, my colleagues also pointed out that a lot of what was being interpreted here was if we go from a landscape with no trees to a landscape with total tree cover, and we look at groundwater, we expect a decline. And this is definitely what those 506 observations showed. There was a decline. But this dotted line here, is that true? Is that what we expect, that when we plant some trees here, we get an immediate decline? This is the implication of what that Economist headline was, what that Nature headline was. This is what the donors were being told by that information. So perhaps the line is something more like this. Why would it be like that? I won't go into too much details, but there's this concept called infiltration, the ability of the landscape to absorb water. And some colleagues at least thought that the role of trees and vegetation in actually capturing water in the landscape as opposed to having it run off would be crucial. So this is a theory, and I'd like to report that in 2016, finally, this has been confirmed, at least in one site. This is very detailed work, and I won't go into all the details. Some of you know how complicated this kind of work is. But they did 3 years of research looking at how water was used in the landscape with scattered tree cover in a site in Burkina Faso. This is a site where a lot of the rainfall falls in intense showers. A lot of that rainfall then runs off from the landscape and disappears into rivers and is no longer available. And as I say, not going into too much details, I guess the key thing is here. You can see this is canopy cover or tree density. Here is 0. So you start down here and you look at what happens when you put a few trees in the landscape. You immediately get a lot more water captured in the landscape. And this is based on empirical data. There's a few assumptions here about how you scatter them in the landscape. Densities can be done in different ways, and you get different relationships. But the point is, more trees, more water capture in the landscape. If you go up to 100% tree cover, which you never get in this landscape, it will be lower. So eventually it will drop down. These all peak and they drop. But the point here is, if you see the difference, if you start from 10 here, going up to about 5 times in one relationship, or 6 times, these are not small differences. We're talking about the landscape being able to hold 5 or 6 times more water. So huge benefits, you can imagine, for the people who live here. We can actually talk about planting trees as a good thing for water in these landscapes, or trees are good for keeping water in these landscapes. So we don't actually have to have the donors telling us not to plant trees, not to keep trees. So it's a positive story. And I think what's really striking here is this is only 2 years ago, and we're still arguing about these things. There's a huge opportunity if we want to talk about water in these landscapes, looking at these relationships better. This is just one place. Just one place. So there's still a lot to discuss. Okay. The main topic today will be rainfall, I think. So switching to rain. Rain is obviously what most people depend on for their water. And if we look around the world, it's not just that people need water, they also want reliable rain, because if you have too little or too much, you can have catastrophes. And if you look at global figures, you see millions of people have died in droughts and floods, and a lot of emergency aid following from those kind of events. And I guess if you look in the news media over the last few years, it looks like many of these things are becoming more frequent, more catastrophic. So we have a problem of reliability of rainfall, not just water, but reliability of rainfall. Okay, we're going to talk about rain. Where does it come from? Just to highlight how little water is really in the atmosphere at any one time. We're talking about a very small fraction of the mass of the atmosphere. 1/4% of the mass of the atmosphere, approximately, is water. And if you actually looked at that as a liquid layer across the entire Earth's surface, it's less than 3 centimeters. So you can imagine how vulnerable this is. This is what we all depend on, this little layer of water. It's very vulnerable to things that might change those values. Now I find talking in Europe, a lot of people assume that most of the rainfall comes from the ocean. This is definitely true in Norway, definitely true in Ireland, where I come from too. So just to highlight the fact that a lot of rainfall comes from the land surface. So I can't reach up there, but you see in the top it gives you the units, thousands of cubic kilometers per year. I just like to highlight these units because they simplify, thousands of cubic kilometers per year. How much water is falling on the Earth's surface every year? These are approximate numbers, of course. About 113,000 cubic kilometers per year falls on the Earth's surface. Of that, only 40,000 cubic kilometers are coming from the ocean. So you can see 40 is a lot less than 113. So where is the rest coming from? Well, of course, it has to come off the Earth's surface. So this is basically rainfall that falls on the Earth's surface, re-evaporates, to the atmosphere and falls again. So we're talking about water that's been recycled. And you can see this is 73. So it's approximately twice, almost twice as much as we get from the ocean. This is something, I mean, it's always the case in climate science that people debate figures, so you can also find other figures. And I found a more recent one, for example, 2017. But the basic proportions are similar. And some of these changes are due to land cover change as well. But basically, it tends to be that kind of pattern. Most of the rainfall on the Earth's surface is coming off the Earth's surface. That's the point here. Now, we can understand these things much better also in terms of locations. It's not just the global picture, but also location specific. So how do we do this? Well, now we have amazing data available to actually look at things in a more specific local. This is just a beautiful slide to make the point that we have amazing data. So this is just over a small number of hours in one period in July in 2009. And what you're seeing is the moisture coming off the ocean surface. And we have these kinds of data sets now because of satellite imagery and the capacity to generate huge data sets and understand things like where moisture is coming from. So we do have this amazing knowledge, increasingly. And it allows us to do things like what I show in this slide here. So the top left is showing rainfall patterns across the land surface. It's pretty much what you would expect. The black color, you can see up there, the key is about 2 meters of rain or more per year. So you see this band across the equatorial tropics, the black band top left there, 2 meters or more. And then the deserts being blue, places where you get maybe less than half a meter of rain per year. Up there in Europe, it's somewhere in the middle, about 1 meter or so of rain per year. Okay, so this is fairly clear. We have good data on this. We now also have relatively good data on the sources of moisture coming off the oceans and the land surface. And this map shows you from the land surface what you're getting back to the atmosphere from the land surface. And you can see again that in the equatorial tropics, we have high amounts of water coming off, up to 1.5 meters per year, typically in the equatorial forests. Drier parts of the world, less water coming back. We can put this information together moment by moment, hour by hour, across the Earth's surface, make assumptions, combining with wind directions, combining with where rain is occurring, and talk about which places on the Earth's surface are dependent on water coming from where. We can do this moment to moment, and then we integrate it across the entire globe over longer periods. So here, this is based on more than, well, what is it, 18 years of data. Sorry, no, 9 years of data, 9 years of data. What this lower map is showing you is which places are dependent on water coming off the Earth's surface. So some places are much more dependent than others. So if we look here, say northern China, most of those farmers are very dependent on water that originates elsewhere in Asia, perhaps in Europe, perhaps to some extent in North Africa. So these guys are very dependent on water coming off the Earth's surface to the west of them. The same in the Sahel. You can see that these places are very dependent on water. You can see the key here, about 80% of their moisture perhaps coming off the Earth's surface. There's quite a few Brazilians in this room, and they will know that down here in Sao Paulo, Rio de Janeiro area, also they're very dependent on moisture that's re-evaporating off the Amazon rainforest. So you can see to some degree how people would be vulnerable to land use change upwind. Yeah? As a source of moisture, you are very dependent on having that moisture coming to you. One of the other recent advances, it was a study published just in 2013 in Nature. And I just like to highlight this because when we're talking about this re-evaporation of the Earth's surface, I think for a long time we assumed that vegetation played a small role or a minor role. People generally talked about 25% of the moisture coming through plants in an active way. And in 2013, that changed with this study in Nature telling us that actually it looked more like 80 to 90%. I don't need to go into the methods, but it was based on isotopes in water. So it was quite a striking change, several times more water coming through vegetation than we previously assumed. This is not just in wet parts of the world, but also in dry places where there may be very small numbers of trees, but because of their deep roots, like here's a tree in the Kalahari Desert with roots going down to about 70 meters, they're able to access deep water. just to say that all these numbers are, it's science, so it's controversial, so people have debated, and you can see the main author there is also involved in a revision here. He's the second author here. Somebody complained about some part of the calculation, and they adjusted. So it went from 80 or 90 to 70 plus or minus 14. Okay, it's gone down a bit, but it's still a lot more than we previously thought. So these are still active areas of research. There's still things we don't know the exact numbers, but we know vegetation is much more important than we previously thought. 5 minutes, good. So forests, we know that forest is a major source of this atmospheric moisture we've been talking about that other people are depending on for their rainfall. We know that when we lose forests, there are typical consequences of that's been recorded in many places around the world. Often there's less cloud, often rainfall becomes less reliable, and that's been seen in many parts of the world. Also, people have done these global studies looking at how land cover has influenced the availability of water, and the story is a negative one. So one estimate recently was that vapor off the land surface has already declined by 5 to 6% due to changes in land cover. This includes deforestation, drainage of wetlands, irrigation schemes, all of that included. So that's the global number. And remembering that 2/3 of the world population is already suffering from water shortages, a decline of 5 to 6%, I mean, it depends where it is, of course, but you can think that that could have quite negative consequences. So here's just one example of the kinds of patterns we have from around the world. It's a study I was involved with. So here's the island of Borneo. The equator runs through here. This green area is an area that's still forest in 2010, and the red area was forest in 1973, but has been lost up to 2010. So we have quite dramatic loss of forest cover in that period, 1973 to 2010. And if we look at rainfall, you can see here the scale, daily rainfall, and we see how it changed. 1950 to 1970 was reasonably constant. Then we had large-scale clearance of the forest. And we start with, it's a noisy data set, and this is relatively typical. It's one of the problems we have trying to interpret. But it's quite a dramatic decline, more than 20% decline. And if you look at this also by area, the parts of Borneo that have had higher deforestation have higher declines, implying, of course, that forest loss is a cause of this. But it doesn't tell us what the mechanism is. But it's relatively typical. There have been a number of studies like this. So let's look at forests as a source of atmospheric moisture in slightly more detail. And just to go back and remind that tropical forests evaporate between 1 meter and 2 meters, in some cases more than 2 meters per year. That's a huge amount of water. Big source of moisture. They're more effective than most other vegetation types by a large amount, particularly by low vegetation types. Grassy vegetation cannot compete, generally about 10 times less. And a key point is that forests are more efficient even than open water in actually evaporating moisture to the atmosphere. The amount of water vapor per hectare of a forest is higher than you would even get from open water. How are they so effective? Well, I think the easiest way to explain it is it's a bit like why you hang clothes on a clothesline if you want them to dry rather than putting them flat on the ground. You can think of the leaves on the end of the branches being like clothes on a clothesline, flapping in the turbulent air. That movement in the faster air, the turbulence, allows moisture to be carried into the atmosphere much more effectively. You have such a leaf area in the trees, in the forests, that it allows a much more effective emission of moisture. So forests are particularly special for a number of other properties, not just the amount of water they can emit, but earlier I mentioned infiltration, the actual idea that these landscapes with tree cover can actually capture moisture. We call that infiltration. Often the soils in forests are also good at storing water, so it's available for the trees to actually then re-evaporate it to the atmosphere. Trees in particular have deep roots, particularly when compared with most other vegetation. This is just an example of the deep roots. So they can access water deep in the soil profile. You can imagine the soil surface being dry even for several meters, but the trees are able to access the wet soil below. Trees are large compared with other vegetation, and the stems of trees are full of moisture, and that moisture is also a source of water that can be evaporated to the atmosphere. And that is accessible to the tree to actually evaporate. And if you actually measure a stem during a hot sunny day, on a dry day particularly, you will see that the stem shrinks. The tree shrinks as moisture is actually lost from the stem. Of course, it's replenished eventually, but trees can maintain that stream of moisture when other vegetation cannot do that. Aerosols I won't talk about because Antonio will talk about it. Just some specific numbers. How does water get deep into the middle of continents has been a particular question. You can think about the Amazon River. You have this huge amounts of water, 209,000 cubic meters per second flowing out of the river. And then you think, wow, that's a lot of water. Where does that all come from? And of course, over time, the amount that's coming out has to be balanced by a similar amount coming in. And the only way we can understand this is by thinking about the atmospheric sources of moisture. And I just like to quote the Nobel Prize winner, some of you probably recognize. He says, the answer is blowing in the wind. So we really need to understand this question by understanding how winds work. I'm going to jump a couple of slides. Just, you probably all understand how it works, right? The heat and the winds. Air rises, draws in air. I'm assuming you learned this at school because I need to jump. It's also how we understand how the climate system works. Basically, it's a very simple idea that the air rises over the equatorial tropics. Almost ended, right? Yes. Okay. So the global climate system is basically depends on a temperature gradient. And even though this idea goes back to the 17th century, Edmund Halley, who's a contemporary of Isaac Newton, so this is an idea with a long history, we've made it more complicated because we understand many things much better. The observations we have are much better. We talk about cells, we talk about rotation and Coriolis and all these things. We've made it more complicated, but the basic driving force in the modern climate system and the understanding of the climate system is temperature. Okay, so I'm going to come to the last slide now, because it's going to lead on to what Anastasia talks about. It's just to say that we have this wonderful understanding, very sophisticated models, very convincing models in many respects. They have some shortcomings. And this is a study published by two people who work with models, Stevens and Boney. These are IPCC authors, so very respected people, and they wrote an article in Science a few years ago, and they still say these things. It's just that this is a nice quote, so I like to use it. They wrote an article called What Are Climate Models Missing? And they said, okay, I'll just read this. Rainfall over land is largely determined by unresolved processes. This is the main limitation in current representations of the climate system and a major roadblock to progress in climate science. So you have the people who are working in the IPCC, making models, talking about how we understand the climate system. They're telling us they don't understand how rainfall works. That's the message. And if you look at recent articles by the same guys, they're saying the same things. It's not that we've had a radical improvement. That's not the case. This is really the state of the art in global climate science. We don't understand how rainfall works. We should be talking about this more. Okay.